Imagine that dark matter, the invisible stuff that makes up 5/6 of all the matter in the universe, isn't a swarm of heavy particles at all. Imagine instead that it's a wave, a single quantum wave, so light and so stretched out that one wavelength spans thousands of light years, and an entire galaxy sits inside what is effectively one giant quantum object. That's not science fiction. It's a serious testable theory called fuzzy dark matter. And for the past several weeks, we, one human and a small team of AI research agents, have been doing something unusual with it. Taking the 3 landmark simulation papers of this field and reproducing them. Not summarizing them, rerunning them, line by line, halo by halo, failure by failure. I'm your host, and with me is the physicist who's been living inside these simulations. Welcome.
Thank you. And I want to set the stakes honestly right at the top. Reproduction is the unglamorous half of science. Everyone celebrates the discovery paper. Almost nobody goes back and checks whether an independent team with independent code and independent choices gets the same universe out. We decided to check for 3 of the most cited papers in wave dark matter. Some things reproduced beautifully. Some things reproduced only after we understood our instruments better. A few things did not reproduce, and one claim of our own we had to retract along the way. All of that is in this episode because the failures taught us more than the successes.
I love that we're promising failures up front. But let's build the physics first. When I hear dark matter, I picture the standard story: WIMPs, weakly interacting massive particles, little heavy things drifting through space. What makes fuzzy dark matter different?
Almost comically so. A WIMP in the classic picture weighs about as much as 100 protons. The fuzzy dark matter particle, an ultralight boson often motivated by string theory axions, weighs about 10 to the minus 22 electron volts. Let me say that differently. It is roughly 31 orders of magnitude lighter than a proton, a 1 followed by 31 zeros. And in quantum mechanics, mass sets your wavelength. The de Broglie wavelength goes as 1 over mass times velocity. Make the particle absurdly light, and its quantum wavelength inflates from subatomic scales to, for typical galactic velocities, about a kiloparsec. 3,000 light-years. The particle's quantum fuzziness becomes galaxy-sized.
So the quantum weirdness that normally lives inside atoms gets blown up to astronomical scale.
Exactly, and that has a gorgeous consequence. On large scales, tens of megaparsecs, the cosmic web of filaments and voids, fuzzy dark matter behaves just like cold dark matter. Same web, same statistics. But on small scales, below that kiloparsec wavelength, the wave nature fights back. Quantum pressure, really the resistance of a wave to being squeezed below its own wavelength, halts gravitational collapse. So the theory makes a package of sharp predictions. No tiny halos below a minimum mass. Structure formation delayed because small things can't collapse early. Interference fringes, literal quantum stripes, running through galactic halos. And at the center of every halo, the showstopper, a soliton.
Soliton is one of those words physicists say with reverence. What is it here?
It's a standing wave of dark matter, a smooth, dense, coherent core where quantum pressure pushing out exactly balances gravity pulling in. A hydrogen atom's ground state, except the binding force is gravity and the object is the size of a galaxy's heart, containing maybe 100 million suns. It has a universal density profile, one family, one shape, characterized entirely by one number, its radius. Squeeze a soliton to half its size, and its central density goes up 16-fold. Density scales as radius to the -4th power. Its mass scales as 1 over its radius. These rigid scaling laws are what make it falsifiable. And observationally, it's attractive because real dwarf galaxies do look like they have smooth cores, not the sharp density cusps that plain cold dark matter simulations prefer.
Okay, now the equations, spoken, because this is radio. What actually governs this stuff?
2 coupled equations, and they're old friends from undergraduate physics glued together. First, the Schrödinger equation, IH bar times the time derivative of psi equals minus h bar squared over 2m, times the Laplacian of psi, that's the kinetic wavy part, plus m times phi times psi, where phi is the gravitational potential. Second, the Poisson equation. The Laplacian of phi equals 4 pi g times the density. And the density is just the wave function's squared magnitude, so the wave moves in the gravity field. The gravity field is sourced by the wave's own density, a self-gravitating quantum wave chasing its own tail. That pair, Schrödinger-Poisson, is the entire theory. Everything in this episode is that pair of equations, solved in an expanding universe at brutal scale.
And the brutality is the point, right? Why is this so much harder to simulate than ordinary cold dark matter?
Because of a cruel joke the mathematics plays. In ordinary dark matter simulations, you track particles. Where matter clumps, you need resolution, and where it's empty, you don't. In fuzzy dark matter, the wave oscillates everywhere, and here's the cruel part. The faster the matter moves, the shorter the wavelength you must resolve. Deep inside a massive halo, velocities are high, so the wave crinkles into fine granules. You need exquisite resolution exactly where the most matter is moving the fastest. And the time step shrinks with the square of the grid spacing. Halve your cell size, and each step costs 4 times more steps. That scaling, time step proportional to grid spacing squared, is the villain of this entire story. Remember it because it's about to kill several of our simulations.
Foreshadowing noted. Now the papers, 3 landmarks. Give me the tour.
Paper 1, Shive, Chiwei, and Broadhurst, Nature Physics, 2014. The first simulation ever to resolve this theory's full cosmology. They used a code called GAMER, Adaptive Mesh Refinement, meaning the grid sharpens itself where the action is. Running on GPUs. 2 megaparsec box, resolution down to 60 parsecs. And they saw the whole package. The cosmic web looking just like cold dark matter on large scales, solitons sitting in the center of every single halo, the interference fringes, core dwarf galaxy profiles matching observations. It made the theory real.
And paper 2 is the sequel.
The companion, Shive and collaborators again, physical review letters, same year. This one distilled the physics into one law, the core-halo relation. In words, the mass of the central soliton grows as the halo mass to the 1/3 power and scales inversely with the square root of the cosmic scale factor. That 1/3 exponent, call it beta, became the field's most tested, most fought-over number. The paper also explained where the law comes from, with 29 soliton merger experiments, and derived the minimum halo mass, the floor below which quantum pressure forbids collapse. About 3 times 10 to the 8 solar masses at redshift 8.
And paper 3 brings in normal matter.
Motz and collaborators, Physical Review Letters, 2019. First simulation to marry fuzzy dark matter waves with gas, baryons, the stuff of stars. Their headline was about how structure grows differently. In cold dark matter, the smallest things collapse first, then merge upward. In fuzzy dark matter, the first structures are filaments. Cosmic strands collapse as coherent objects, and they found something exotic living inside them. Cylindrical solitons. A standing dark matter wave shaped like a cable with a specific dimensionless mass per length constant, they measured as 0.127, and they showed the wave interference imprints itself on where the first stars form.
3 papers, 1 theory, escalating ambition. Now, who is we? Because our setup was unusual, and I think listeners will find the machinery as interesting as the physics.
The team was 1 human director, making the scientific calls, controlling the budget, green-lighting every paid run, and 3 AI research agents, each owning a lane. Agent 1 ran GAMER, the original paper's own code, plus all the reporting. A public website that became our system of record. Agent 2 built and ran Jaxion, our own differentiable wave solver. Hold that word, differentiable, it becomes the hero of the 3rd act. Agent 3 ran Gadget 4, the standard cold dark matter code, as the control experiment. 3 independent codes, because if 2 completely different numerical methods agree on a soliton, it's physics. If only 1 code sees it, it might just be a bug wearing a costume.
And the discipline, you had rules.
Rules that were mechanical, not aspirational. Every measurement pre-registered before running an experiment we wrote down in a file committed before the data existed, the estimator, the cuts, the random seeds, and the success criteria. No changing the question after seeing the answer, no post hoc bias corrections. If a control failed, we diagnosed it. We never subtracted a fudge factor to land on the expected number. Failures got published on our site with the same typography as successes, and every number on every chart traces to an archived script anyone can read. The reason is simple. Reproduction work is worthless if the reproducers are allowed to fool themselves. We are as foolable as anyone, so we built the guardrails first.
Right, Act 1, Gamer, the paper's own instrument. Where do you even start reproducing a nature physics paper?
You start by building their world. We compiled Gamer for modern GPUs, generated cosmological initial conditions with the fuzzy dark matter power spectrum, the recipe for the infant universe's ripples with the small-scale ripples erased below the quantum cutoff, and validated that generator against published transfer functions to 0.1%. Then we ran their 2 megaparsec box. 3 times, actually, 3 independent random universes, 3 seeds, because one realization proves nothing.
And solitons?
Everywhere, 94 resolved cores across the 3 boxes and several epochs, and each one wears the predicted universal profile, the Shive profile, which in words says density equals central density divided by 1 plus 0.091 times radius over core radius squared, all raised to the 8th power. That awkward 8th power is very steep. The soliton has a definite edge. It's not a fuzzy blur. We fit every core, checked the internal consistency between core mass and core radius that the soliton family demands, and the fits agree with the paper's law with a correlation of 0.81. First pillar, reproduced.
You make it sound smooth. Was it smooth?
The solitons were smooth. Our instruments weren't, and I want to tell one story because it captures the whole campaign. To measure delayed structure formation, the claim that fuzzy dark matter's first halo collapses around redshift 13 versus redshift 50 in cold dark matter. We needed a detector, a piece of code that watches a 30 megaparsec simulation and calls out honestly when the first real halo has formed. Our first version had a subtle flaw. It diluted density peaks when it downsampled the adaptive grid. Version 2 fixed that and broke something else. Version 3 we validated end-to-end. Here's the discipline point, the estimator, what counts as a halo, which threshold, which mass definition, was pre-registered and never changed. What changed was the optics of the instrument, and each iteration was documented. That distinction, fixing your telescope versus moving the goalposts, is everything in this game.
When the telescope finally worked?
Redshift 15.7, first collapse, seed 1. We then ran 2 more committed seeds, 14.4 and 14.4 again. The paper said about 13, in a box with different volume and their own single realization. Bigger boxes catch rarer, earlier fluctuations. Our numbers bracket theirs exactly as the statistics predict. Compare that with redshift 50 in cold dark matter, and the reproduction is unambiguous. Fuzzy dark matter delays the dawn of structure by hundreds of millions of years. That's finding number 8, replicated 3 times.
You said a seed got disqualified once. That's the quarantine story?
Yes, and I insist on telling it. During the replication campaign, one seed's output showed a halo that existed at one epoch and had vanished at the next. Halos don't evaporate. That's physically impossible, so it had to be forensics, not physics. We traced it. A job launch fault had let 2 simulations right into the same directory, interleaving 2 different universes' snapshots. The entire lineage was declared contaminated, quarantined, excluded from every result. And a fresh seed was run from scratch. Total honesty cost, about $30 and a day. The alternative, a corrupted point silently sitting in a published figure, is how fields end up with irreproducible literature. The vanishing halo was our canary, and I'm genuinely proud we caught it. And one more from that box, because it's my favorite pure physics result of the campaign, the minimum halo mass. The theory says quantum pressure sets a floor. Below roughly 3 times 10 to the 8 solar masses, nothing can collapse, ever. We tested it with a discriminator we declared before looking. A genuine virialized halo must have a central density at least 1,000 times the cosmic mean. Wave granules, transient quantum knots that look like halos to a naive halo finder, hover around 40 times mean. We ran it at redshift 8 and at redshift 6. Every single candidate below the predicted floor turned out to be a granule. Every genuine halo sat above it. The quantum floor is real, and it's visible in our own data.
Beautiful. Let's cash in the foreshadowing. The 1/3 law, beta, the crown jewel. You had 94 solitons. Fit a line through core mass versus halo mass. Read off the slope. What could go wrong?
Everything, and it's instructive. Our first attempt gave beta equals 0.03, essentially zero slope, with an r² of 0.0. Complete washout. And the reason is embarrassing only if you don't think it through. A 2 megaparsec box is tiny. It only manufactures halos in a narrow mass range, about 1.5 decades. Measuring a 1/3 power law needs lever arm. You need dwarfs and giants on the same plot. We had only dwarfs. The original authors knew this. It's exactly why their PRL stacked simulations across 2, 20, and 40 megaparsec boxes and multiple epochs. One box at one epoch simply cannot see the law. So the crown jewel needed either their multi-box stacking or bigger boxes. And bigger boxes bring us to the wall. But first, the detour that saved the measurement, Jaxion.
Act 2. Agent 2's lane. Why build your own solver when Gamer exists?
3 reasons: independence, cross-code validation. Speed of iteration, Jaxion is a spectral solver, a few hundred lines of clean mathematics. Split-step Fourier, kick-drift-kick, unconditionally stable, conserving mass to machine precision. And the third reason is the strategic one. It's written in JAX, which means it's differentiable end-to-end. You can ask the simulation, if I nudge the boson mass, how does every observable respond, and get the exact derivative through the whole nonlinear evolution, by automatic differentiation, not a finite difference approximation, the exact gradient. File that away, it becomes the payoff of the whole episode.
And with this shiny new instrument, you attacked beta.
We attacked, and we hit our second wall, subtler and more interesting than the first. Jaxion is a uniform grid code, every cell the same size. We ran boxes at 512 cubed, 1024 cubed, 2048 cubed, 8.6 billion cells, our hero runs. And then measured carefully the resolution question, is the soliton core actually resolved? The answer at every affordable resolution was no. The core radius sat at between 0.5 and 1.5 grid cells. Always. You can't measure the radius of something 1 pixel wide. And worse, as you push resolution, the halos themselves deepen, velocities rise, the cores shrink. The target recedes as you approach it. We proved with a convergence study that no affordable uniform grid resolves cosmological solitons at this boson mass. That negative result, chart F1 in our series, redirected everything.
I want to pause on that because a lesser team buries that chart. You led with it.
It's the most useful chart we made. It says every naive attempt at this measurement is fooling itself, and it forced the creative move. If the simulation can't resolve the core, get the core from mathematics. The soliton isn't an arbitrary blob. It's the ground state of the Schrödinger-Poisson system. So we built a solver that finds that ground state exactly. Imaginary time evolution. You take the Schrödinger equation and let time run in the imaginary direction, mathematically substituting time with -I times tau, which turns oscillation into decay. Every mode of the wave function decays at a rate set by its energy, so the excited states die fastest, and what survives, when the dust settles, is the pure ground state. The soliton, computed to arbitrary precision on a dedicated fine grid, no cosmology needed.
The universe's ground state, extracted in a bell jar. Did it match?
To better than 1% against the Shive profile, and it reproduced the soliton family's scaling laws, mass proportional to 1 over radius, the mass to the 4th power relation between soliton mass and central density to 5 significant figures. That validated solver became our core oracle, and then the measurement strategy flipped. Instead of asking the blurry cosmological simulation to show us the core, We fit the known exact soliton shape to the blurry data, using the parts of the profile the grid does resolve, the shoulders and wings, to pin down the one free parameter. We proved on synthetic data that this fitting recovers the true central density even when the core radius is only 2 cells across. That's the trick that unlocked beta.
So now you fit all your halos with the oracle.
And one more gremlin appeared, this one statistical, and it nearly fooled us. When we applied a quality gate, only fit halos where the core is at least this resolved, the measured beta drifted upward as we tightened the gate. 0.3, 0.5, 0.7. Which pattern screams resolution bias? Maybe the real answer keeps climbing and we can't trust any of it. Before believing the alarm, we simulated the alarm, Monte Carlo experiments where the truth was beta equals 0.3 by construction, with realistic scatter and realistic sample sizes. The synthetic data reproduced the same runaway. Tighter gates mean fewer halos mean noisier fits, and the noise, filtered by the gate, masquerades as drift. The runaway was small number statistics, not physics. That vindication, chart F7, is what lets us state the headline with a straight face. Beta equals 0.30 plus or minus 0.03. The paper's 1/3 recovered independently.
And the crosscode moment, you called it the strongest single validation of the whole campaign.
Chart F9. Take Gamer's 3 resolved Zoom cores, completely different code, adaptive mesh, different discretization, different everything, and place them on the soliton family diagram. Central density versus core radius, where the exact family is a power law with slope -4. Gamer's cores land on it with a fitted slope of -3.95, and the family constant, density times radius to the 4th, agrees to about 10%. 2 independent numerical universes, one soliton. When 2 telescopes built by different teams see the same nebula, the nebula is real. That's when I stopped worrying that any of this was numerical artifact.
Which brings us to the villain you promised, the wall. Set the scene.
The scene is the 20 megaparsec box, the one big enough to give beta its lever arm directly in Gamer, the direct measurement in the paper's own code. Everything the campaign wanted converged on that run. We launched it as a zoom, modest resolution across the full box, with adaptive refinement concentrated on one massive halo, Halo B, the kind of setup that in cold dark matter would be routine. It started gorgeously, and then, around Redshift 12, the code hit its patch ceiling and died. Gamer organizes refinement into patches, blocks of 8 cubed cells. Our GPU's memory budget allowed 1 million patches. The simulation, entering the granule regime we discussed, fine quantum structure demanding refinement exactly where matter concentrates, wanted 2.3 million and climbing. We tried Halo A, died at Redshift 12.05. Halo C, same wall, same epoch, 3 halos, 3 corpses, same cause of death, memory, not speed.
And this is where I remember you saying the time step villain returns too.
Both villains, hand in hand. Even if memory were infinite, the time step shrinking with grid spacing squared makes the final stretch to Redshift 0 excruciating. But memory was the immediate executioner, and here's the part I find scientifically delicious. We measured the wall. 6 different instruments, the single GPU zooms on 3 halos, the uniform grid convergent ceiling, an experimental hybrid scheme that promised bigger time steps and delivered a 19-fold under-dense core, a resimulation strategy that starved halos of their surroundings. And the rest, each with a quantified failure point. Nobody publishes feasibility maps of where simulations die. We think that map is one of the campaign's genuinely novel contributions.
But you broke it. Tell the break.
The break was arithmetic, then engineering. If one GPU's memory allows 1 million patches and the physics wants several million, buy 8 address spaces, recompile Gamer for MPI, message passing, 8 ranks, each rank owning 1/8 of the universe with its own patch budget. 11.2 million patches of headroom, 5 times what killed the serial runs. We provisioned a machine with 8 H100 GPUs, rebuilt the code, which took 6 build failures in one long night, missing MPI-aware Fourier libraries, header paths, one self-inflicted wound where a careless global text substitution corrupted the build system's guard expressions, and silently dropped the MPI sources from compilation. All documented in the ledger, all fixed. Then we launched, from the last surviving checkpoint of the Halo B zoom, at redshift 19.
And it crawled.
It crawled, 7% CPU utilization. Our launch had spread the 8 ranks without granting them their thread teams, so each rank ran single-threaded. The director actually caught it before we did. He looked at the throughput and asked pointedly whether we were wasting the hardware. The fix was one line of processor binding. Each MPI rank pinned to 8 physical cores with 8 OpenMP threads. Throughput jumped roughly 20-fold, and overnight, this is now last night in real time, the run swept down through the graveyard. Past redshift 12.05, where Halo A died. Past 11.5, where B and C died. Past every tombstone, 0 faults, and as we record this, it's grinding through redshift 9. In territory no simulation of this configuration has ever reached, with checkpoints streaming to storage every few hundredths of the scale factor.
The wall was memory, and distributed memory beat it. But there's a twist about the GPUs themselves, the hardware confession.
The confession is that the GPUs are nearly idle, a few percent. What we're actually renting for $24 an hour is the chassis, the aggregate memory and the CPU cores. The Wave Solver's kernels fire too briefly at this problem size to load the accelerators, and that inverts the field's folklore. Everyone assumes these simulations are GPU-bound. They're memory-bound and thread-bound. If you're a graduate student planning a fuzzy dark matter zoom, our advice, measured, not guessed, is provision patch capacity and cores. A CPU build on a high-memory node costs a third as much. That's a methods finding worth a paper section on its own.
So MA finishes tonight or tomorrow and delivers the direct beta. Meanwhile, the merger question, the PRL's mechanism, you ran that too.
Running as we speak, and the story so far is a corridor and caveat story. The PRL explains the core Halo lore through mergers. When solitons collide and relax, the surviving core's mass relates to the system's energy per mass through a proportionality constant alpha, which their 29 experiments found to be constant. We pre-registered the same test, soliton pairs, controlled mass ratios, measure alpha across the ladder. In our uniform grid pilot, mergers only complete their relaxation within our box and time budget for a narrow corridor of configurations. And inside that corridor, alpha was not constant. It rose from about 28 to about 40 as we scaled the system, a 9 sigma trend. Inconclusive negative, but with an honest asterisk. The paper's own experiments used isolated boundary conditions with adaptive refinement, a genuinely different regime from our periodic uniform pilot. So we built their regime, isolated boundaries, refinement on, and that grid's final run completes tonight. Alpha's verdict in the paper's own arena lands with it.
Act 3, the differentiable adventure, and I'm told this one contains a funeral and a resurrection.
A funeral for a method, a resurrection for its purpose. The dream, differentiable adaptive mesh refinement. Combine Gamer's trick, resolution only where needed, with Jax's trick, exact gradients through everything. If it worked, you could resolve solitons cheaply and differentiate through structure formation, the best of both worlds. Phase 0 and 1 worked. Gradients flow through a soft, differentiable refinement criterion in 1 and 3 dimensions. A refined soliton evolves correctly with valid gradients. Phase 2 worked. A cosmological box with automatic differentiation derivatives verified against finite differences to a ratio of 1.00. Then Phase 3, a dynamical soliton living below the coarse grid's resolution, with a fine patch meant to capture it. The fine patch starved. It recovered 1 to 3% of the reference core. The information the fine grid needs was never present in the coarse field it refines from. We diagnosed it with surgical experiments, one-way coupling tests that falsified our leading hypothesis about boundary conditions, and concluded it's not a bug. It's a structural limit of the two-field scheme. We wrote that up, parked the method with dignity, and pivoted.
And the resurrection?
The purpose of differentiable AMR was never AMR. It was inference, measuring the boson mass from data. And it turned out the uniform differentiable solver plus the Soliton Oracle, could deliver that science without the fancy refinement. We built the full pipeline. Fisher forecasting, using those exact gradients, tells you the information content. A 10% core density measurement constrains the boson mass to a few percent. Simulation-based inference, training on Jackson forward models, actually recovers the mass to about 5% from mock observations. And the crucial credibility step, simulation-based calibration. You inject hundreds of known truths, run your full inference on each, and check that your claimed uncertainties are honest. Our 68% intervals contain the truth 69% of the time. Uncalibrated posteriors are astrology with error bars. Calibrated ones are instruments.
And with a calibrated instrument, you get to say something spicy about the theory itself.
The spiciest thing in this episode. Fuzzy dark matter at the classic mass, 10 to the minus 22 electron volts, is in serious observational trouble, and our pipeline reproduces the trouble quantitatively from our own simulations. Dwarf galaxy cores want a light boson. The cores are big, and big cores mean long wavelengths, low mass. The Lyman alpha forest, absorption lines from hydrogen strands backlit by quasars, tracing small-scale structure at high redshift, wants a heavy boson because it sees no suppression where a light boson would erase structure. Run both constraints through the calibrated machinery, and they collide at 7 to 9 sigma. The romantic version of this theory, one boson explaining all the small-scale puzzles, is very likely dead, and that's not a rumor, it's a reproducible calculation. The theory survives at higher masses or with extra physics, but the fairy tale version doesn't.
Which makes reproducing the foundational papers more important, not less. You want the record straight before the field moves on. Speaking of the record, Moch, the hydro paper, and the retraction you promised.
First, the successes. The exotic object, the cylindrical soliton living inside filaments, we reproduced fully, and the process was pure philology plus physics. We derived the cylindrical ground state ourselves, measured our filaments, and initially disagreed with the paper's number. The resolution came from reading the paper's own source files. The author's fit convention differed subtly from the naive one. Adopt their convention, rerun, and our constant is 0.1257 against their 0.127. Agreement to 1/3% plus a lesson. Reproduction sometimes requires reproducing the author's definitions, not just their physics. Filament first collapse, reproduced in 3 of 4 seed universes, with the honest note that it's a tendency, not a law. One seed collapsed not first. The fringe spacing prediction, interference stripes set by the de Broglie wavelength, passes within a factor of 2 in both regimes we tested, which is the paper's own standard.
And the funeral bell.
2 negatives, stated plainly. First, their stellar suppression claim, that fuzzy dark matter forms about 40% fewer stars than cold dark matter in matched volumes. We tested it with our gas-coupled runs and measured a ratio of essentially 1.0. Not reproduced in our setup, possibly a resolution or volume issue on our side, possibly not. The chart is public either way. Second, the retraction, which is ours alone. Early in the campaign, we ran a gas plus dark matter simulation and published on our own site a finding that the gas traces the dark matter web, with a correlation coefficient quoted. A later audit, part of a systematic cross-check pass, found the correlation had been computed in a way that inflated it. Recomputed properly, the gas web coherence was under 10%. The gas in that run never actually coupled to the web. We retracted the finding, struck it through publicly with the reason attached, defined a coherence gate any future gas claim must pass, and moved on. It's the only claim we've had to retract, and the audit that caught it is now standard.
I genuinely think the retraction is the best advertisement for the whole enterprise. Now, Act 4, briefly, the control universe. Why does Gadget 4 matter so much?
Because every claim we've made tonight has the form. Fuzzy dark matter differs from cold dark matter thus. That sentence is empty unless you own the cold dark matter side too. Same volumes, same seeds where it matters, same analysis code. Agent 3 validated Gadget 4 at full scale first. 100 megaparsec box, 500 million particles, Halo mass function agreeing with the standard theory to better than 1% across the full mass range, power spectrum tracking the nonlinear standard to the grid limit. Then the matched 20 megaparsec control for our contrast. That's what let us do the flagship sim versus sim measurement. Divide our fuzzy dark matter power spectrum by our cold dark matter power spectrum. 2 real simulations, no analytic stand-ins. And watch the ratio sit flat at 1 on large scales, then dive at the quantum cutoff within 20% of the analytic prediction, shifted in exactly the direction nonlinear evolution predicts. The lane also ran a subtle hybrid, cold dark matter dynamics on fuzzy initial conditions, which cleanly separates how much suppression comes from the initial ripples versus the ongoing quantum pressure. Unglamorous, indispensable.
Before the scorecard, I want the backstage tour because most listeners have never heard what it actually costs, in money and in operational grief, to do computational cosmology on rented hardware. Give me the economics.
With pleasure, because the numbers are shockingly small by the standards of the field, and the grief is shockingly specific. Total campaign spend so far, about $1,600 of cloud compute, plus the flagship mission currently running, which will land somewhere around another $1,500. For that we got 3 validated 2 megaparsec universes, 3 30 megaparsec first collapse replicas, a 500 million particle cold dark matter control, 8 billion cell hero runs, 27 merger experiments, and the wall-breaking zoom. A single postdoc year costs 40 times that. The economics of this kind of science have genuinely changed, and the constraint has moved. Money is no longer the scarce resource, judgment is. Which run to buy, which to kill, which negative result to trust enough to stop. Every one of those calls was a human decision, made on evidence the agents prepared.
And the grief. You promised grief.
Operational war stories, each with a scar and a lesson. Every paid run carries a watcher, a small guardian program that checks the simulation's pulse every few minutes. Is it alive? Is it producing sane numbers? Has the memory demand crossed the red line? Has the spend crossed its cap? If anything trips, it kills the run, harvests the data, and shuts the machine down to stop the meter. Those watchers saved us real money. One caught a dying run within minutes and prevented an idle machine from burning a weekend. But automation cuts both ways. One night, during planned surgery on a running mission, we were deliberately relaunching the code with better settings. The watcher woke up mid-operation, saw the simulation gone, concluded death, and dutifully shut down the machine while we were mid-keystroke on it. The machine was following its instructions perfectly. The instructions just hadn't imagined a surgeon. Since then, the protocol is anesthetize the watcher first, operate second. Every one of these incidents is written in the ledger because operational honesty and scientific honesty are the same muscle.
I also heard something about checkpoints being the real insurance policy.
The deepest ops lesson of all. The flagship run banks a full checkpoint, the entire quantum state of the universe, terabytes across the campaign, every 0.25% of cosmic expansion streamed off the machine to durable storage. That converts catastrophe into inconvenience. A crash at Redshift 9 costs us hours, never the mission. Our first Zoom attempt, weeks ago, taught this the hard way. It died at the wall with sparse checkpoints, and months of simulated cosmic history evaporated with the process. The relaunch that's running right now was possible at all only because one checkpoint from the old campaign had survived at Redshift 19. We restarted civilization from that save file.
Now, the record itself, you keep saying the ledger, the site. Describe what a visitor actually sees, because I think the apparatus is a result in its own right.
The site is organized into 4 lanes, 1 per instrument, and each lane has the same anatomy. A results tab, numbered evidence cards, each one chart plus its claim, its provenance, and its identifier. The identifiers are immutable, so a card can be cited from anywhere and the citation never rots. A lab notes tab, the scored record, every paper claim as a row, its status, and crucially an evidence column that is the living, honest summary of what we actually found, kept current as results land. And as of this week, a code tab, every script that produced any result, organized by the finding it produced, readable inline, each file carrying a plain language header of what it does and links to the exact result cards it generated. Claim to chart to code, 2 clicks in either direction. We built it for a working session with a professional cosmologist who's agreed to look at the record, the conversation that decides whether this becomes a collaboration. But the deeper reason is philosophical. A reproduction of published science should itself be reproducible, or we've just added another layer to the problem we set out to fix.
Suppose the beta verdict lands clean tomorrow. What's actually left between you and a complete reproduction? And what would it take to go all the way to the present-day universe, Redshift 0?
3 tiers in escalating ambition. Tier 1 is nearly done. Tonight's missions close the direct core halo measurement and the merger mechanism, which takes the headline lane to 11 of 12. Tier 2 is the honest residue, claims anchored at Redshift 0, like the exact present-day satellite density comparison and the Milky Way soliton's velocity signature. Our data reaches Redshift 7, extrapolating to 0 via the paper's own scaling is legitimate but labeled, and finishing it properly means simulating another factor of 8 in cosmic expansion, through the era where the time-step villain, grid spacing squared, remember, is at his cruelest. On our current architecture, that's multiples of everything spent so far. Tier 3 is the frontier the papers themselves never reached. Bigger boxes, gas physics, star formation, the boson masses the observational tension actually still allows, closer to 10 to the minus 21 electron volts, where every length scale shrinks and every cost multiplies.
Which raises the supercomputer question. You've been renting 8 GPUs at a time. The original authors had national facilities. Can you rent your way to Redshift 0, or do you need the big iron?
The honest answer has a fork in it. You can rent surprisingly far. Commercial clouds now offer multi-node clusters, dozens of GPUs with fast interconnect, that are functionally rented supercomputers. Our code already speaks the protocol they require, and a few $1,000s of that would buy Redshift 2 or 3, where most of the remaining claims live. But the scaling isn't infinite. The physics concentrates all the refinement into one small violent place, and beyond a handful of nodes, the machines wait on each other more than they compute. The true Redshift 0 run at scale is a national facility allocation, free at the point of use, awarded by proposal, requiring an academic principal investigator, which is exactly why the collaboration conversation matters. And here's the pleasing circularity. The strongest exhibit in such a proposal is precisely a public, pre-registered, honestly scored reproduction record with a broken wall and a feasibility map. The apparatus we built to keep ourselves honest turns out to be the ticket to the bigger machine.
One more physics question before the scorecard, because I don't want listeners to leave thinking the tension killed the whole idea. If the classic mass is in trouble at 7 to 9 sigma, what survives?
A family of retreats, each with its own character. Heavier bosons, 10 to the minus 21 electron volts and up, evade the Lyman alpha constraint but shrink the solitons, giving up much of the original charm of explaining dwarf galaxy cores. Mixed models, part fuzzy, part cold, dilute both the predictions and the constraints. Multiple axion fields, self-interactions, and richer dark sectors are all leave. What our campaign contributes to that debate is not a verdict on the theory, it's confidence in the toolkit. We now know with receipts that the simulations underlying all of these predictions can be independently reproduced, where their instruments are trustworthy and exactly where they aren't. Whatever mass nature chose, the field's computational foundations are sounder tonight than they were a month ago, because somebody checked.
This is a tutorial as much as a story, so before we land it, I want the drill. Rapid fire recap. I name the concept, you give it back to me in one breath. Equations in words, no hiding. Ready? The master equations.
Schrödinger-Poisson. 1 I bar deep C dt equals minus h bar squared over 2 m Laplacian psi plus m phi psi. 2 Laplacian phi equals 4 pi g rho. 3 rho equals psi squared magnitude. Wave feels gravity. Gravity is sourced by wave. Everything else in this hour is consequences.
The de Broglie wavelength and why it's the theory's ruler.
Lambda equals h over mv, Planck's constant over mass times velocity. At 10 to the minus 22 electron volts and galactic speeds, that's about a kiloparsec. Below lambda, quantum pressure wins and structure is erased. Above it, gravity wins and the universe looks cold. One ruler, drawn at galaxy scale, is the entire phenomenology.
The soliton profile?
Density of R equals central density over 1 plus 0.091 R over RC squared, all to the 8th power, one free parameter, and the family rules: mass inversely proportional to radius, central density proportional to radius to the minus 4, soliton mass to the 4th power proportional to central density, rigid enough to falsify,
The crown jewel law?
core mass proportional to scale factor to the minus 1/2 times halo mass to the 1/3. In plain speech, bigger halos wear bigger hearts, but only as the cube root, and earlier universes wear denser hearts. Our measured 1/3 exponent, 0.30 plus or minus 0.03, with the direct in-code measurement finishing as you listen.
The minimum halo mass?
Quantum pressure forbids collapse below roughly 3 times 10 to the 8 solar masses at redshift 8, measured in our own boxes by the 1,000 times mean virialization bar. Below the floor, only granules, never halos. Fuzzy dark matter predicts a universe with no small change. No pennies, only bills.
The time step villain, one last time, because he's the reason this took GPUs and grief.
The stable time step of a wave code scales as the grid spacing squared, halve the cell, quadruple the steps, and the wave demands finer cells precisely where matter runs fastest. Cost explodes as the 4th power of resolution or worse. That single scaling built the wall, priced redshift 0 out of a single GPU, and wrote most of the checks in this episode.
And while we're in tutorial mode, the granules. We've invoked them all hour as the villain's foot soldiers. Give them their 2 minutes of physics.
They deserve it because they're the theory's fingerprint. Inside a halo, the dark matter wave isn't one smooth standing wave. It's thousands of wave packets with random phases, crisscrossing at the halo's velocity dispersion, and wherever they overlap, they interfere. Constructive here, destructive there. The halo's interior becomes a boiling speckle pattern, granules, each about a de Broglie wavelength across, each flickering on a crossing time. They're not objects, they're interference maxima, the same physics as laser speckle on a wall. But they have real gravitational consequences. They jostle star clusters, they thicken stellar streams, they heat disks. Several of the sharpest observational tests of the theory are granule tests. In our simulations, they're both signal and menace. Signal because our zoom images show them at exactly the predicted scale, the fringe test we passed. Menace because to a halo finder, a bright granule looks like a tiny halo. That's why our minimum mass measurement needed the virialization bar. And to an adaptive mesh, they all scream, "Refine me at once," which is precisely how they flooded the patch budget and built the wall. One phenomenon: fingerprint, imposter, and executioner.
Fingerprint, imposter, executioner. That's the episode in 3 words. Okay, now let's land this. Scorecard time. Across the whole campaign, what's the tally and what did the campaign teach?
The tally, as we record, Gamer Lane. 9 of 12 findings fully reproduced, 3 partial with 2 live missions closing in tonight. Jaxion Lane against Mots, 6 full, 5 partial, 3 negative including the 1 retraction. The differentiable thread, a method limit discovered and documented, and a publication-grade inference pipeline delivered on the pivot. Gadget 4, the control validated at sub% level, and 1 wall, formerly believed impassable on affordable hardware, broken with distributed memory and a feasibility map to guide whoever comes next.
And the meta lessons, the ones that outlive this particular theory.
4, I think. 1. Reproduction is instrument science. Most of our failures were telescopes, not physics, and the discipline that saved us every single time was separating pre-registered questions from evolving instruments. 2. Negative results steer better than positive ones. The convergence impossibility chart and the wall map redirected months of effort. Charts of failure are navigation. 3. Independence is the only real validator. 2 codes, 1 soliton. That's worth 100 convergence tests within 1 code. And 4. Honesty is cheap and compounding. The quarantine cost $30. The retraction cost a strike-through. Both bought us the standing to say the word reproduced and mean it. There's a fifth, about the human and agent's mode of working. The pre-registration and the public ledger weren't just good science. They were the coordination protocol that let 3 AI agents and a human share one body of evidence without stepping on each other's claims.
And tonight, while listeners finish this episode,
An 8 GPU machine is grinding a 20 megaparsec universe through Redshift 9, on its way to 7, in territory nothing of its kind has reached, carrying the direct measurement of the crown jewel law. A merger grid is finishing the alpha verdict in the paper's own regime. Early core fits from the freshly banked snapshots are already streaming in. And every one of those results, success or failure, will land on the public record with the script that made it, the pre-registration that predicted it, and the chart that shows it, whichever way it goes. That's the whole method. And honestly, it's the most fun I've ever had checking someone else's work.
the universe as a wave, 3 landmark papers put to the test, 1 wall down, 1 number still cooking overnight. When the direct beta lands, we'll be back with the verdict. Until then, the ledger is public, the code is readable, and the solitons, we can now say with confidence, are real. Thanks for listening.
Thanks for having me. Go look at a dwarf galaxy tonight and remember, its heart might be a single quantum wave, holding itself up forever.